All right, I'm starting streaming, and today we'll focus on graphs, and particularly we'll be focusing on an algorithm to find the shortest path. So I got new notes, done, and also new homework and stuff like that. So it's all good. Let's get rid of the other stuff that we don't need. Yeah, we're doing Dijkstra's algorithm today. Okay. And I think today's the tablet is going to come in handy because we have to draw a few graphs and stuff like that. Except it has not been cooperating last week. Alright, 440. A. Oh, you guys are studying that in another class, right?
Raj.
Yeah.
Yep. Okay. Well, just keep in mind that this one may not be the same as his. There are like slightly different ways to represent it. Okay, so let me see if I can get my lecture note thing to go first, because this way I can start to draw pictures. I can illustrate things a little bit better. School.
Do you need to set up the
440.
microphone, or is it fine like that?
You mean the mic?
Yeah, like does it need to be standing up, or is it fine?
It's already set up to be omnidirectional, so I think it will still record just fine.
Oh, okay.
But this way is slightly better. Okay, so we'll see whether this works or not. Find devices, select. Okay. What happened last week was I was able to make the connection, but nothing would show up on the PC side. Nope, today's fine. So these are the kind of things that kind of bugs me all to no end. Is someday it works, someday it doesn't work, and I could not figure out the pattern of why it works and why it doesn't work. Okay, so we'll focus on the homework assignment first, and then we'll go back and talk about the graphs and stuff. So the homework assignment is here. It is not. Oh, I opened a new tab here. Okay, so I'm going to go into edit mode because it's not entirely done yet in terms of the description of the homework assignment. And we'll go ahead and make this as big as possible. Okay, so what we have here is a graph. We'll talk about what a graph is in a little bit more detail later. The vertices are A all through G. So A, B, C, D, E, F, G, those are your vertices. And then you have edges represented by arrows going from one vertex to another vertex. So one edge is only connecting one vertex to another vertex. Okay. Now there are also questions of whether a vertex can go back to itself using an edge. So can you have an edge going from A back to A? In theory, yes, but in practice, usually practical problems do not have self looping edges. Okay. All right, so you see the numbers on the edges. Those are the cost of an edge. So it will cost you 1 unit to go from vertex F to vertex C. Okay, that's basically a cost. It will cost you 4 units to go from vertex A to vertex C. It will cost you 3 units of something from vertex A to vertex B, and so on. Is that okay? So what I'm missing in the description is what are the destinations, or what is or what are the destinations. In Dijkstra's algorithm, interestingly, you can track multiple destinations at the same time. And that's one of the really cool things about Dijkstra's algorithm, is you can do that. Okay, so in this particular homework assignment, we'll go ahead and track at least 2 destinations. So we'll go ahead, I'm going to go here and say destinations are, okay, let's pick something that's interesting as a destination. Okay, so we can pick C as a destination, and we'll also pick E as a destination. Okay. So basically, I'm designating C, this guy here, and E, which is this guy here, as destinations. I want to find out, what are the shortest paths from every vertex to at least one of the destinations.
Including the destination vertices?
Including the destination vertices. Yep.
Just out of curiosity, are the lines one directional or are they both?
They are one direction. So this is a digraph, or known as a directed graph. There are such things as undirected graphs, but they are not as usual. You can always emulate an undirected graph using a directed graph, because an undirected graph basically means if there's an edge between vertex A and vertex D, for instance, then you can go in either direction.
Like there's two equal paths?
Yep, exactly. So you can emulate it by having two equal edges, in a digraph to emulate. So you can have a digraph to emulate the effect of an undirected graph. Yep.
And let's just trace the algorithm using the table in the HTML editor. I was wondering what does Q and E mean.
Aha! Okay, so that's something that we're going to talk about.
Okay.
And we'll go through at least one example using a different graph, okay, today, so that we can at least get some practice with that algorithm. Okay? But is the homework assignment itself sort of clear what we're trying to do?
Yeah.
Yep.
No implementation?
No because it's already implemented no implementation in a programming language, so you don't have to turn in anything that runs. If you're in another class where your professor has a different homework assignment, you can use it if you want to, but you still have to fill in the table, so you have to kind of change your program to kind of spew out things to fill in this table. Is that okay? I can see certain smiles. He's like, I know how to do that. Yep.
You said we're tracing from every vertices, so you would start with like A and then do it for C and then E, and then you would go next to B and then do it for C and then E.
There's a particular order, when you use Dijkstra's algorithm, there's a particular order to do things. Okay, so let's say you're in a park, okay? So you're in the middle of a park somewhere, and you need to go to the bathroom, okay? Typical scenario, okay? And you want to go to a proper bathroom, okay? Not one of those trees and whatnot. So you look up the map, okay? Go like, okay, we got bathroom here, 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 and here, and you're at a certain spot. So all the bathrooms are quote unquote destinations. So you have to figure out, okay, which bathroom is the closest to me, and how do I get there? That's basically your question. And Dijkstra's algorithm can answer that question. But the way it answers that question is by using a breadth-first search. This is a very good example of an algorithm that makes use of breadth-first search instead of depth-first search. So what it does is, imagine that it starts with every single bathroom, and it starts to make bigger and bigger circles with the centers being the bathrooms, okay? Until one of those circles touches you. Then it'll go like, oh, okay, that bathroom is the closest to you, and this is the path to go there. Okay? Is that sort of okay or not? Okay? So I'm not sure about the algorithm you used in the other classes. Does it deal with multiple destinations, or can it only deal with one destination?
I took 430.
Okay. Okay, so is anyone taking 430 this semester? So have you done the Dijkstra's algorithm yet? Not yet? Okay.
You'll be starting it soon then, for sure.
Huh?
I said they'll be starting it pretty soon then.
Okay.
Yeah.
Oh yeah, it has to be
was this time of the year.
pretty soon, because
Yeah.
I think we only got like 1 week.
It was
one
like the
week
last
left.
thing we covered, the shortest path algorithm and everything. It's like the last thing that a rush covers before the final.
Okay.
Yeah.
So that would kind of jive with what we talk about in this class, even though the algorithm may be slightly different.
Yeah.
Okay, cool. So we go back here, and then we open this slide here, and nobody has a chance to watch it yet, because I just got it done like earlier this morning. I started on it last night, and I decided that typing on that little tiny keyboard on my tablet was not the most efficient. Especially when you use VI and it doesn't have an escape key.
Oh no.
It can still do it by control, open square bracket, which means the same thing as escape. But because the keyboard is really small, the placement of some of the keys is off, just enough that you keep pressing the key and go like, no, the other one, the one next to it. So it was not very effective. I just have to kind of get used to it. All right, so this is new. We are going to talk about what a general graph is. Okay, so here we have a discussion of what a graph is, at least from the mathematical perspective. The graph itself is known as a two-tuple, which is basically because it has two components. The first component, V, is a set of vertices, and it has a separate component, which is E, which is a set of edges. So a graph is defined by vertices and edges. There's little restriction of the set of vertices. In other words, as long as it is a set of something, you can call that your vertices. It can be a set of integers, can be a set of real numbers, can be a set of coordinates, okay? It doesn't really matter, okay? As long as it is a set of something, each element of that set can be called a vertex. The nature of the set of edges kind of depend on whether it is a graph, whether the graph itself is directed or not. So in the case of a directed graph, or digraph in short, the set of edges is a subset of the Cartesian product of vertices times vertices. Which means each element of E is a two-tuple. The first element or the first item of the two-tuple is where we're going from. The second one tells us where we're going to. In other words, an edge is always connecting a vertex to another vertex.
So that's why we use tuples instead of sets.
Exactly, because when you use a set, then the ordering is not important. But when you use a two-tuple, then you have a starting point and you have an ending point. Okay, but what is interesting is the first item is called the tail, and the second item in the two-tuple is called the head. Now this term seems to be very reverse because, hey, we're starting from the first item to the second item. How come the first item is called the tail? It's because of the way we draw an arrow. Okay, so these terms, tail and head, refer to the tail of an arrow and the head of an arrow. So remember that when you kind of look at the terms. Okay, so recall that ordering is significant in a tuple. An edge of a digraph is usually drawn as an arrow going from the tail, which is the first item of the two-tuple, to the head, which is the second item of the two-tuple. So getting back to our homework assignment here, okay, so we have an edge from A to B, right? So the two-tuple corresponding to that is just open paren, A, comma, B, close paren. That represents this particular edge here, the edge that has a distance of 3. Is that okay? Okay, cool.
You're talking about those, depending on the arrow, do you have to start with, does it matter which order you represent those in? So could you say BA and AB?
In this particular graph, you only have AB,
okay,
but not BA.
Gotcha.
In fact, there are some vertices that are not directly connected by edges. Like there are no edges between B and C. So there are no edges in either direction between B and C. But is B connected to C? Yep, they're connected. You can go from B to F and then go to C. They're connected, but they're not connected by a single edge. All right. Any other questions at this point? Okay, questions? So we go back to, I keep forgetting that I just need to switch a tab in the browser. Okay. So a graph may be undirected. When you're dealing with a graph that is undirected, you can always look at it as a directed graph where the following restriction applies. If AB being an edge in the set of edges, if and only if BA is also in edges. If you can find a particular edge going from one vertex to another vertex, it means the other one has to exist too. The one that is going in the opposite direction has to exist, and typically they have the same distance. Is that okay? Do you guys still remember what we talked about the other day? I used a map, a Google map as an example, where the intersection, each intersection is a vertex, and then the connection between adjacent intersections is an edge.
Yes.
So do you think in that case it is better to use a digraph, or is it better to use an undirected graph? Does it make any difference whether you're going in this direction or the other direction? It does. Okay, now in Sacramento, for the most part, it doesn't make as much difference, but if you live in San Francisco, especially downtown, then oh yeah, it makes a big, huge difference. Exactly. They have a lot of one-way streets. Now, with a one-way street, it doesn't mean there's no way going backwards. It's just that the distance or the cost of that path is extremely high. It is high enough that most people will say, nah, it's not worth it. Except for a life or death situation, then you go like, okay, we might chance it just once. All right, so we'll go look at, just one single term, okay? Before this semester, I always go through all the terms related to graphs, like what is a walk, what is a trail, what is a blah, blah, blah. But this time I have decided to kind of focus on the algorithm itself, so we only talk about the path in this case. So a path is a graph. In a graph, is a tuple of vertices. Okay. Now there are various definitions of what a path is, but in this case, I just want to call it a tuple of vertices. Or if you want to, it is a list of vertices. It is an array of vertices. Okay. So ordering is important within the tuple, within the array, within the list. Okay. And in this case, I'm going to use lowercase p to denote such a tuple of vertices. In other words, lowercase p in this case is a path. Then edges must lead from one vertex to the next within the path. In other words, this has to be true for p, if p is to be called a path. So let's take a look at this, what this is saying. So I'm basically looking at I being a member of natural numbers. And I really should be using math BB, but I forgot to use math BB to denote the n here, so it doesn't look like the n with a double bar, vertical double bars. But basically, I is a natural number. If I is less than bar p bar, which is the number of items in p, minus 1, then I really care about whether the second part is true or not. What if I is not less than bar p bar minus 1? In other words, what if I is not a valid index? And I don't care. It's an implication, right? For any implication, if the first part is not true, the whole thing is true. Which also means in this case, I only pay attention to the second part, which is this part here. If I only pay attention to this part if I is a valid index. But I is not just a valid index. It can only go from 0 up to the second last item of the path. Because when you look at the requirement that I wanted to fulfill to be true, I want p bracket I, which is the one of the item in the path, and p bracket I plus 1, which is the one vertex that's next to that one. I need the edge. I need those two vertices to form an edge that is in the graph to begin with. So in this case, uppercase E is representing the set of edges for that particular graph. Is that okay or not? I really should be a little bit more clear. A path in a graph, and then the graph is G equals to VE. So this way it is much more clear that E is referring to the edges of that particular graph. Are we doing okay or not?
So can you go over the second part of the application again?
The second part of the implication?
Yeah.
This part?
That's the one that's important.
Yep. So the core of this whole thing is this part here. That's the whole core. The rest is really just saying, okay, what indexes are we talking about? But as long as I is an index and I plus 1 is a valid index, then we need pi, which is a vertex, and pi plus 1, which is another vertex, which is the one right next to pi. We need an edge to connect those two. And that's why, when you look at the parentheses, these parentheses are not optional. They are not really only here for grouping purposes, because this forms a tuple. It forms a two-tuple, which is representing an edge. And that edge has to be an element of the set of edges. Yep.
So, for an example, in the problem you gave us, it goes from A to G. So P is everything from A to G that's connected?
Nope. Okay, so that's a good question. I got two things that I want to do. The first one is go back and fix the notes so that it is clear what this E is representing, and also fix this N so that it is the natural number N. So I'm going to do that first. Uh-oh. Cannot resolve.
Is the name server down?
I hope not. Nope, name server is up. That is not there. Is it ddns.net? I think it is. Okay. Yep, so no IP is not up and running. Dynamic DNS, that's what DDNS stands for. But apparently it is down, so I can't change the notes at this point. That's okay, it's kind of optional. All right, so what we want to do is to look at an example. Okay, so I'm going to switch to the tablet here, and we'll use a different example. So we'll have, vertex A, vertex B, vertex C, vertex D here, and we'll make this, make it 5 vertices, so that we have 5 vertices here. And we'll say that A goes to C, C goes to B, B goes to E, and then A also goes to E directly. And let's make it a loop here. So B goes back to A, like that. Okay. And D is on its own. Okay. D is not connected, but it is a part of this graph. So the first thing we want to do is to figure out, okay, so if this is the actual graph, how do we represent it using that notation that we talked about earlier? This is the graphical notation, which is great for visualization. But when you're dealing with graphs that are really complicated and there's a high connectivity between the vertices, the graphical representation is no longer intuitive because you can't easily follow edges anymore. But for small ones, this is great because we can actually figure out what is going on. So in this case, G is VE again. Okay, so this allows me to write the V and E separately. So V itself is a set. Now it is important to remember that V is a set and not a tuple, because the ordering of these vertices in here is not important. In fact, I'll make it very clear that it is not important by saying B, A, D, E, oops, bad penmanship there, C. Okay, so I think this really kind of helps to indicate that this is a set where how you want to list the members of this particular set is not important. The order is not. Is that okay? And then the second set that we are interested in is E. So E is the set of all the edges. So in this case, E would be, I'm trying to be random again here. So we have CB as a 2-tuple being a member of that set. We have BE, okay, so BE. We got AE, and then we also have AC. So I'm just wrapping around to the next line here, AC. So 1, 2, 3, 4, 5. We got 5 edges, and they're all here. Is that okay? Is this helping to connect between the graphical representation versus the kind of more mathematical notation? Yep.
You forgot BA.
I forgot BA?
Yeah, it's like there's only 4 edges there.
Okay, I miscounted then. Okay, so we got BA. Thank you. All right. So it is a set of 5 elements. Thank you for the correction. So we're doing okay so far with the notation versus the graphical representation. Okay. What about D? Well, it's okay. No one says every single vertex in the graph has to be connected somehow to another vertex. That is not a requirement.
Has an edge in it.
No, it has no edge. But for algorithmic consideration, you can probably look at it as having edges of infinite cost to all the vertices. Yep.
So each of these edges has a value, right? Like A to C, maybe
Yeah.
1.
Yeah,
So how do
we
you
can
represent that with?
With a graphical representation here, we can just assign numbers, right? So I'm gonna use this for other things later on. So we'll try to assign some kind of interesting values. So we'll make C be with a distance of 4, distance of 1, distance of 6, distance of 1 again, and for this one we'll have a distance of, this one doesn't really matter. We'll have a distance of 2. Is that okay?
So how do you represent it in the set notation?
Now in the set notation, okay, let me switch back to the notes here. So switching back to the notes, we usually would define a distance function where we are mapping the domain is the set of edges, and then the range is the set of all the real numbers. So that's how we do it. We basically use a function to say that. So in this case, okay, so in this case, if I were to kind of really draw that out, D itself is a function, but remember in this class, a function is a set. It's a set of 2 tuples. So we have, okay, so we'll pick out BA first. So the edge BA, which is BA, has a cost of 2. So we are mapping the edge BA to the number, to the real number 2 here. Now, even though I only assigned integer values, in the example, there's no reason why they cannot be real numbers. So they can be like 2.65 if you want to, Okay, so we'll pick another example here, maybe AC. So the edge AC has a distance of 1 associated with it. So I'm not going to list all of them because that's just going to be a little bit tedious. But that's how we can represent the distances. It is its own function mapping the edges to real numbers. So we still do okay so far with this example. Cool. So I'll just let you guys, write notes because I think a few people are still writing something. So now the big question is, how do we find the shortest path from any vertex to one of the destination vertices? Yep. You can use a tree. Well, the tree is kind of a byproduct. So we can, this is not a tree, right? It is quite obvious it is not a tree because a lot of vertices have 2 incoming edges, which you cannot have with a tree. So once we find the shortest path, you can find what we call a shortest spanning tree, but at this point it's not a tree yet. Okay? So the algorithm cannot depend on tree concepts because we're dealing with a graph that is not a tree yet. So we use one of 2 algorithms. There are 2 well-known algorithms that can get this done. One is called the Dijkstra's algorithm. You can easily look it up online as well. So when you look up Dijkstra's algorithm, D-I-J-K-S-T-R-A, that's the guy's last name, Dijkstra's algorithm. Dijkstra is an interesting fellow too. He Alan Turing was the original father of computer science. Between Dijkstra and Knuth, those are the 2 quote-unquote modern fathers of computer science because they each contributed a lot to algorithm designs and the formal analysis of computer stuff. So you can look up Dijkstra's algorithm. This is even slightly animated to kind of show you how exploration occurs in Dijkstra's algorithm. And you can also look up the algorithm itself. So you can look up, okay, let's see, where is it? Pseudocode. So the pseudocode here, this is a much more complex example. It basically shows you how it determines. The red lines are the ones that are quote unquote determined, okay? And then the blue line is representing things that are quote unquote being explored. So it's kind of an interesting way to look at it. But I got a better analogy that is easy for you guys to remember, even though it might be a little gross. But gross things are easy to remember because your mind goes like, ew, and now I remember that. Yep. Okay. So this is Dijkstra's algorithm in pseudocode, and I have my own. Okay, so when we go back to my own notes here, which is, nope, that's the blog from another class. Okay, so when we get back to here, so this is my version of Dijkstra's algorithm. It's a little bit messy because I'm trying to integrate English explanation comments, directly into the pseudocode. So that's why it looks a little messy. But the indentation indicates nesting. Okay. All right. So obviously, there's no need to copy this particular part because it is already in the notes. So I might make some additional changes later on, but the algorithm is already here. All right, so the best way to look at this is to look at a maze, okay? So think of a lab environment. So the best way is to look at this. Okay, let me switch back to the notes here. Okay, so the best way to look at Dijkstra's algorithm is to think of it as a maze, okay? So we'll go ahead and actually turn this into a maze. We'll have some dead ends here. Don't know exactly how complex we want to make it. But yep. Yep. I can actually dig up what we call micro mouse mazes. Okay, this is kind of interesting too. Okay, so micro mouse is a robotic competition where student teams, usually of students, will make autonomous, fully self-contained robots, and they put it into these mazes. You see some pictures down here, like right here. So you basically put a robot that is programmed into one of these mazes, and you always start at a certain point. So cell 54 is usually where we put the mouse, and then the destination is always at the center. So these 4 cells are called the destinations. But the configuration of the maze is not known prior to the competition to the mouse, to the robot. So the robot has to explore the maze while at the same time trying to figure out how to get to the center 4 cells as quickly as possible. And that's the nature of the competition. So it's kind of interesting. I used to teach that class over at Davis before they had a major financial issue. If you guys remember, many years ago, I would say about 7 or 8 years ago, they had a major financial issue, so they had to let go of all the adjunct lecturers at that time. So I got my Friday back. Yep.
How many spaces are they allowed to test while they're looking around? Or are they allowed like second 2 or 3 rounds, or how do they do that? They
have mechanical size limitations, but not height limitation. So if you want to, you can actually make a post and have a video camera to look down and look at the entire thing. But then you need optical processing and stuff like that. When the micro mouse competition was started, it was back in the maybe late 80s or early 90s. So we cannot pack that much processing power onto a circuit board about yay big. The footprint of a mouse is, if I remember correctly, it is 20 by 20 centimeters or something like that. So it's not really that big. Each cell is only about 25 by 25. I cannot remember the exact size, but it's not that big. The biggest limitation is actually battery power. Back in those days, you can pack a ITX motherboard with enough processing power, but you cannot pack enough batteries to keep it running for long enough to do this. Now these days it's a whole different story because the newest Arduinos are 32-bit processor based, and you know, a lithium-ion battery can keep it running for at least half an hour. But one computation is only about 10 minutes. So things have changed a lot since the beginning with these things. So you know, back in those days, even if you could physically put a camera on top, there's not enough processing power to process the image itself. So, and also back in those days, cameras are a lot more, they're heavier, and the resolutions are lower too. So maybe these days it can be done, but you know, back in those days it was not a solution. But these days you have a lot more possible ways of solving this. So I just want to point this out because you know, some of you may go to a university where they still participate in micro mouse competitions. It's really fun. So getting back to here. So I'm going to finish this little maze here. And then we have maybe a dead end here. We have another snail shell. Snail shells are kind of interesting. Okay, so we have a maze, and then what we do is we designate certain spots as quote-unquote ground zero. Okay, those are your destinations. So we'll mark several things which I'll mark in red as your destination. So we'll say this one, this is a destination here, and the destinations do not have to correlate to, you know, in terms of are they next to each other, or you know, where are they on the map. So I can call this one another destination, and we'll call this one another destination. So the red squares are denoting, you know, what cells in this maze are designated destinations. Okay, so switching to another, back to black first. Okay, so Dijkstra's algorithm start from the red squares. Okay, and then it goes outward. So imagine that these are the places where you put, you know, insecticide bombs, or insecticide, you know, emitters, or whatever you want to call those things. Okay. So any, you know, cockroach in a red cell will die instantly from time zero. Makes sense, right? Because they're at ground zero. You know, that's exactly where the insecticide is released. So we basically mark those. Okay, I'm going to use green here with 0. Okay. Because the red squares are the destinations themselves. They have a distance of 0 from a destination. Does that make sense? Okay. So everything that is right next to a red square, it has a distance of 1. So this has a distance of 1. This guy has a distance of 1. This guy has a distance of 1. Distance of 1. Distance of 1. Distance of 1. And then you go from 2, right? So, but in this case, with this particular vertex here, it already has a number. So even though it is next to another vertex that has a number of 1, I'm not going to update this because the new number of 2 is more than the old number of 1, so I don't have to update it. So now we have 2, we have 2, 2. Oh, I forgot this one here. So there's a 2 here. There's another 2, 2, 2, 2. Okay. Sorry? Yep, there's another 1 here, so we have a 2 here and a 2 here. There we go. But you get the idea of how we assign numbers, right? So from the numbers, or from the cells that just got a number of 2, we will look for the cells that should be labeled 3, and then we go from the cells that were labeled 3 to label the cells right next to those as 4s, and so on. Okay? So that's the nature of Dijkstra's algorithm, but only presented in a planar kind of graph. A planar graph is one that can be represented on a single plane, so that all the vertices and all the edges can be drawn without overlapping stuff. And something like this is naturally a planar graph because it is all representing something that is in 2D space. So are we doing okay so far with this? Okay. So when you look at these numbers, I'll do one more iteration for the 3s. So we got 3, 3, 3, 3, 3, 3, 3, 3, Okay. Okay, so I think I got all the 3's here. So basically, you keep doing this until every single cell has a number. Every single cell that is reachable from a destination has a number, then you're all done. So when this is all done, not only do you know how to go from one particular vertex to one destination as quickly as possible, you actually know the shortest path from any vertex to destinations. Is that okay? Cool? Yep, go ahead.
Did you say, how do we know which one gets priority? So you know that 0 in the, trapped in the corner and the 0 on the right side, how the 2 1s are next to each other?
Mm-hmm.
How do we know, like, since the right side of that 1 could be 2?
Because the 1 got here first.
Okay. And how
Because we drew the 1 after we drew the zeros, right? So this 1 is here because of this 0. This 1 is here because of that 0. So these 2 1s never conflicted with each other because they came from different zeros. But when we expanded from 1 to 2's, this 2 is here because it's right next to a 1. But this doesn't get relabeled as a 2 because the new label of 2 is more than what it already has, which is a 1.
Okay, so the cost would just be 1 if you move 2 spaces, or 2 if you move 2 spaces?
Yeah. So we are not taking turn into consideration. Turning does not cost you anything. But if you look at these orders, and you say, okay, here's a cockroach. When is it going to die? Well, the number of that cell will tell you, when it's going to die. As opposed to another cockroach, let's say here. So if I put another cockroach here, when is it going to die? Well, the number of that cell will tell you, is it going to die before the other cockroach or not? Is that okay? So just remember, if you remember insecticide, cockroaches, and a maze, and just kind of imagine, the insecticide being released at all the zeros, and then you're trying to determine when are these cockroaches going to die. That's kind of the idea of Dijkstra's algorithm. Except in Dijkstra's algorithm, it also accounts for wormholes between these cells. So you can have shortcuts between the cells, and it will still work fine. It will still find out the correct order. Okay? Is that okay so far? Okay, so now that we have seen a kind of more graphical representation of what Dijkstra's algorithm would do, we can now go back to the actual algorithm, which is here. Okay, so now we get back to the really kind of abstract and all the words and whatnot. So we'll start with this, and we'll go slow to make sure that everything is understood here. So we're dealing with a graph. Okay, so the graph that we're dealing with using the typical notation is a 2-tuple of V and E. V is the set of all the vertices. E is the set of all the edges, and also we have a distance function so that we can map each edge to a particular real number as its distance or cost, okay, depending on how you want to call that, but I just call it distance. We will use uppercase S as a subset of V. Typically it is a subset, but nothing says it cannot be an actual, the same thing as V, okay, which means everything is a destination. But this is a subset of vertices identified as destinations. So typically you have at least one element in S. You may have a few, but not the entire V, okay? Because if you have the entire V being destinations, then it's trivial, okay? Everything is a destination. Everything, there's no such thing as shortest path. Everything is already at a destination. So the problem becomes trivial. The algorithm will still quote unquote work, except it doesn't have anything to do. And when S is an empty set, you also have nothing to do. You have no destinations. What am I going to do? There's nothing to do in that case either. So you typically want to have at least one element in S, but not the entire V in S. Is that making any sense? Okay. So the next line says for each v in S, we want to basically define the function L to be 0. Okay, so we're focusing on the third line here. Okay, I'm just going to focus the first part because I think if I highlight the equation itself, it makes it harder to read. So for each v in S, we are defining L, which is a function, L of v, to be 0. Uppercase L stands for length. It really stands for the length of the shortest path going from V to a destination. Is that okay? So that's basically what uppercase L is. It is the length of the shortest path from a vertex V to a destination. Is that okay? If V is a location in the park, this is basically saying how far is the closest bathroom. Now initially, if you're already in a bathroom, that length, the length of the shortest path to a bathroom is 0 because you're in the bathroom already. Make sense? Okay.
The picture you just showed, it started at like 54 or something like that on the maze. So that would be the Google picture that you had?
Oh, that's just, that's reversed. So
yeah,
it
was like starting in. Like
it is reversed. So when you look at this picture, let me see if I can pop the bigger version of this picture here. View image and magnify. Okay. So when you look at this picture, it's reversed because it's not started with 54. Remember, we start from the destination perspective. So we are starting from here. That's our bathroom. This is where you are. So initially, you do not even know that, but after exploration of enough, cells and partitions of the maze, this is your conclusion: is to say, if I start from here, I'm 54 cells away from the destination. Okay, but remember, we are starting from the destination. We're not starting from where you are standing, but we are starting from where you want to go.
Gotcha.
Okay. All right, so getting back to the notes right here. Okay, so the fourth line here is the initialization of all of the other cells. For all of the other vertices. So in this case, V is in the difference between V and S. V minus S will be all the vertices in V, but not in S. Okay, that's our usual set notation from really, really early on in the semester. So for everything that is in V, which means it is a part of the graph, but it is not in S, which means it's not a destination, which basically says V, in this case on the fourth line, represents a non-destination vertex. For a non-destination vertex, the initial length of shortest path to a destination is initialized to infinity. Because at this point, I have not started to do any exploration. And without any exploration, I'm just going to make the most pessimistic assumption and say, oh, to get to a bathroom, it will take me an infinite amount of time. Yep.
So the destination can be rewritten? The destination can be rewritten?
You cannot redesignate a vertex as destination. Is that what you're asking?
Well, I'm just trying to figure out why would you initialize it as infinite? Is it just so that way when it's compared, it just goes?
Because there's no other number to initialize these with either.
Because it might not be possible.
Because it may not be possible. Because you may have a case where each destination is a vertex that has no incoming edges. Then you have all of the other vertices, all the non-destination vertices, really do not have any way to get to a destination. Okay. So is this okay so far? Okay. All right. So the third step is the initialization of Q, which I would call, as an edge set. It's a set of edge vertices where each vertex in Q has just gotten its own L function value updated. Okay. So obviously we got all the L values initialized, but of the initialization to 0 is important. The initialization to infinity is just an assumption. Is that okay? So we put everything in the destination set into Q initially, because we start with those. Is that okay? Yes? Okay. And then here we initialize a set called E prime to be an empty set. So eventually this will become a set of solution edges. In other words, the edges that will end up in E prime will be the edges of shortest paths only. All of the other edges that are not a part of a shortest path will not be in E prime. E prime is going to be a subset of E, and any path made out of edges in E is a part of a shortest path. Is that okay? Sorry. Right? Okay, no problem. So this part here, okay, so now we're getting the actual not the initialization, but the actual algorithm itself. So the overall code of the algorithm is a while loop, which is while Q is not an empty set. In other words, if we still have vertices that just got an update of its length of the shortest path to a destination, we've got some other stuff to do. Okay, because we just got an update, you know, did it change something that we really should be revisiting or we should be re-evaluating? That's what this is asking, okay? So as long as the edge set is non-empty, we'll go ahead and select a vertex V that is a part of the edge set. And this part, okay, let me see if you guys can simplify this a little bit in just tell me what it is. Of course, the next sentence says that, but okay. So let's read this for all W in Q. Okay. In other words, if we have to consider every single element in Q in this case, I want L of V to be less than or equal to L of W. What is that saying about V in relation to everybody else in Q?
It has the shortest path compared to all.
Yep. The known shortest path distance length of V is shorter than okay, there are no shorter paths. There are no shorter paths within vertices in Q than V. There might be ties, but no one has a shorter path. In other words, V is the most promising vertex within this set. And this is why it is called breadth first search, because we examine and expand the most promising vertex. Instead of picking just a random one, we just say, okay, who looks the most promising? You have the shortest path to the destination at this point, we're going to pick you. Okay? So what do we do once we pick this particular V? The first thing we do is we remove it from Q, which means once we select a particular element to quote unquote expand, we take it out of the actual set because now it's explored. And then we do this. Okay, this is bad notation here, definitely bad. I forgot to close the curly brace here, and let me check if I can get back to my server. Nope, still cannot do it. Okay. So if you want to update in your notes, there's a curly brace here to end it, but I can't really do the update at this point. Okay. Okay, so with that imaginary closed curly brace, what is that saying on that for each line? Let me highlight it for each so that we can kind of focus on what it says on that line. Okay, so we are focusing on this particular line here. So what is E? What am I examining here? Now V is already determined at this point. Okay, V is already determined 2 lines ago when we selected the V from Q. So V is not a floating or an unbound variable. What is unbound in this case is W. So what am I saying that I want all the edges from WV in E.
All the edges that have one V distance away.
No, distance is not even a part of this consideration here. We are looking for all the edges such that those edges, how do they relate to V?
They actually like stay next to it.
it connects, exactly. So we're looking for edges, all the incoming edges of V. Okay, that's what we're looking for here. We're looking at all the incoming edges of V. Is that okay? So for every incoming edge of V, it has a source. This is the tail of the arrow, which means, oh, we are going from W to V. So W is the important part here. What are we dealing with W? Well, we are trying to do something like this. Okay, we are trying to do a calculation. Let's take a look at the first part here. L of V plus D of E. What is that telling you? The L of V is the length of the shortest path from vertex V to a destination. That's L of V. That's the definition of L of V. D of E is the distance of edge E itself. But edge E is WV, right? So when you add these two numbers together, what is the significance of that number? One is the length of a shortest path from V to a destination. The other one is the distance from W to V. Okay, so let's take a look at the picture. Maybe that will help. Okay, so switch like that. Okay, so we have some kind of destinations. We don't even care where the destinations are. So we have some destinations. Okay, multiple destinations. And then we have vertex V here. And vertex V has a particular length to one of the destinations. I don't even care which destination. Okay, we just put a dotted line here and just say that between here and one of these things here, okay, I don't know exactly which one, is LV. Is that okay? So we have some squiggly lines going in this direction, but we don't know exactly which one we're going to. It doesn't matter for this consideration. Is that okay? So L of V is the length of the known shortest path from vertex V to the closest destination. Is that subject to change later on? Maybe, okay? But at this point, this is what we know. Is that okay? So now we have a whole bunch of W's, okay? We have a whole bunch of edges here, 1, 2, 3, possibly more, but they are all having incoming edges to V. Is that okay? We look at all the incoming edges to V and we pick one. Okay, now this time it doesn't really matter in which order. We have to look at every single one of these. But at one point we just pick one. Okay, let's say this is our W at this point. Okay, and D, WV is this thing here. Is that okay? So to be more clear, this is D, E, where E is WV. Okay. I'm using the same notation as in the algorithm here. So E is the edge that we have chosen. W is the tail of that particular edge. V is the head of the edge. V is also the same as the vertex that we have picked out from Q earlier. So what is the significance of DE plus LV? So when we look at the distance of this edge plus the length of the known shortest path from V to the closest destination, what is that telling you?
That's the L of W.
It maybe, okay. So that's good. Okay, I like that comment. It may be L of W, but it certainly is a distance, right? A certain length from W to one of the destinations. Maybe the shortest, may not be the shortest, but it is a known distance from a known path. Is that making any sense? Okay. So when we add up these two numbers, D of E plus L of V, it is the length of a path, possibly shortest, but we don't know it yet, okay? It's the length of a path from vertex W to a destination.
So W could already be assigned an L.
Yep.
So you
That's why you have
shorter
to
than
check.
LW. Okay.
Yep, exactly. So this, but this is the significance, but you're right, okay? The significance of this sum is it is the length of a path from W to a particular destination. Which one? We don't really care, okay? We just know that there's a path that exists between W and one of the destination cells. Okay, so I'm switching back to the notes here. So the next thing we do is we check first, okay? Is it less than LW? Well, L of W, is the length of the actual known shortest path up to this point between W and the closest destination. So what we are really trying to say is, did we find a shorter path? Because if this condition is true, that means, yeah, we knew a path, but that is no longer the shortest because we just found a shorter path. Is that okay? So what do we do when we find a shorter path? We do a whole bunch of stuff. The first thing we do is we correct the function itself. In other words, we basically correct ourselves and go like, yeah, we thought that was the shortest path, but it's not. We stand corrected. The shortest path, or the length of the shortest path from W to the closest destination is now this number. Is that making any sense? You found the shortest path, you find a shorter path, you update the length of the shortest path to a destination. So is the highlighted line okay? Should we move on? Okay. So the next line is really kind of confusing. It's basically saying, forget what we knew about that previous path. So the edge that we thought was going from W. Okay. Let me rethink how to phrase this. The edge directly going from W to what we thought was the shortest path should now be removed because it is no longer an edge that is leading from W to the destination. It's no longer a part of that shortest path. Okay. Let's see if we can look at the graph and make it easy to understand. Okay, let me add a new page here. So we'll go ahead and once again use red squares to denote destinations. And then in this case we have W. Over here we have V over here. But in this case there is an existing W, L of W. It already exists, okay? And we say, well, according to what we knew before, we have a path, going from W, and we'll just call this U here. So we say that this is the old way of going from W to one of the destinations, like here. Okay, so we thought. Okay, let me use another color. This was thought to be the shortest path from W to the closest destination. Is that okay? But then we found something. But then we found, okay, V also goes to one of the destinations. So this is one of the destinations. So V also goes to one of the destinations. But what we found was this particular path here, and we're going to use blue here. We found that the blue path has a shorter distance. Is that okay? So what do? We got two things to do. One is we update the L function so that L of W is no longer the way that it was, which is represented by the green line. So the new L value of W is now the value of the blue line. The value of the blue line is DE plus L of V. Okay? So when you look at this thing here, okay, this is D of E, and this part here is L of V. So when you add up these two, it becomes L of W. So that's why we update L of W using this value, because the blue path is shorter than the green path. But the E prime is Yep.
Why are you using the left arrow instead of just equal?
Because equal is confusing. Because equal can mean just comparison, which can be true or false, because we're just asking the question, are these two the same? But in this case, it is not asking whether they are the same or not. We are actually changing the left-hand side to be the right-hand side. So it's an assignment operation and not a comparison. So that's the only reason why I chose to use the left arrow. Okay, but that's a good question. I'm trying to reconnect to my original thought of train. Just got a train wreck. That's okay. No, it's not a problem. I can always do it. Okay, okay, so now we have to remember that when we thought that the green path was the shortest path, this edge, this was in E prime, because we thought that was the shortest path from W to one of the destinations. Yep.
And E prime only consists of the shortest path, right?
Yes.
One thing.
Yep. E prime is only consists of edges on shortest paths. So that's why this one edge here, this one edge W to U was in E prime. But it's not right anymore because this is no longer the shortest path. We found that the blue path is shorter. So we have to take this out. We have to take out this path and then reinsert this path. Okay, wrong color. So we have to reinsert this particular edge. Okay, should now be in E prime. So we have to put this in E prime. Is that okay? So that's why we have to correct ourselves by removing what we thought was an edge from W to the shortest path to a destination. Remove it and then replace it with the new edge, which is WV. Yep.
Is all the stuff from V to the destination in E prime as well?
Say that one more time.
The stuff from V to the destination, basically LV.
Yes. No, L is only representing a single value, which is the length of the shortest path. But you are correct that all of these squiggly things, these are all edges. They're representing a number of edges from vertex V to a destination.
And they're in E prime? They're in E prime?
Yes, they should be.
So then we have to replace those with the ones that were...
You mean these guys?
Yeah. Right.
Nope, not necessarily.
No?
Because we just found a shorter way from here to here, but it does not impact everything that is after W.
We've already stepped through those vertices to get to this point. That makes sense.
So then, I'm a little confused. Does that mean that the stuff from V to the destination is the same as the stuff from U to the destination, potentially? Or?
It has to be less than in order to trigger the update. So L of W, D of E plus L of V has to be less than the existing LW in order to trigger the change. In other words, if I find another path of the same length as what we did before, I'm just going to be lazy and not do a single change. But if I found a shorter path, then I have to do the update. I have to trigger the update. So the real update here, which I'm going to use red again, is to change from the red edge, from the green edge to the blue edge. That's what we're removing is the green edge, and that's what we're adding back is the blue edge.
Right. It just the way it looks on this is that the length from V to the destination looks like it's separate from the length from U to the destination, and by changing the path from U to V, it looks like you're changing an entire path all the way to the destination.
We are only changing where to go from W's perspective. In other words, the path from V to a destination remains the way it was,
Right.
and then the path from U to one of the destination also remains the way that it was. All I'm changing is switching from this to here because the green path as a whole has a longer length than the blue path as a whole.
So this stuff after that doesn't matter at all?
The path after that is not updated, correct. There's no chain updating either, not from this operation. But from this operation, there's something that I have to trigger. Because now that W has a shorter length of its shortest path, has a length that is shorter than what we knew to be the shortest path. Everything that goes to W, they have to be updated now. Because they can potentially be changed as well. So that's what the next loop is for when we go back to the algorithm. So this is why we also have to perform this operation here. So I'm just going to highlight the sentence next to it. Okay, let me bring this up a little bit. Okay, resize. Okay, resize. There we go. This particular window. Update. Oops. There we go. Okay. So this is what the last operation is because W is now updated, I have to put W back into the edge set. In other words, in the next iteration or some future iteration in the while loop, I'm gonna look at W and go like, okay, who is going into W? Because whatever vertex is going to W can potentially have its shortest path updated as well. So, do you see what I mean? So this is where we put things back into Q so that we can reevaluate things as we update something. Is that okay? All right. And when you get out of the while loop, you're all done. Then you can basically define a new graph, which is the solution. G prime has the same vertex as the same set of vertices as the original graph, but the edge is just E prime. So I remember the earlier comment, look at the tree, G prime is guaranteed to be a tree. There's no way it cannot be a tree. And why not? Why do you think G prime has to be a tree, or it has to be a forest? In other words, it has to be, it can have subgraphs, but each one is a tree by itself. Why do you think that is the case?
There's one starting point.
Well, what makes a graph not a tree? What is a tree, and what makes it something not a tree?
Sorry, Mark, because there's only like a single connection after you're done with it between a node and another node.
Yep, I think you got the essence of the answer. That's true. Okay, so when we look at a tree, okay, so in this case, a destination is the destination is a root, okay, of a tree. And you can have multiple trees. You can have a forest. That's fine. But when you look at each tree in the forest, we are looking at something like this. And possibly something like, oops, reverse direction, like that. You maybe even have 3 coming into 1, like so, okay? So G prime has to consist of something like this, which is basically a tree. What will make this not a tree? Okay, so for those of you who are currently in cisp440, did you guys talk about what a tree is? What qualifies as a tree? So what is a tree?
One thing I can think is if it's bounding divided into 2 by what you're graphing.
Right, okay, so I'll add
A tree is a connected graph that contains no cycles.
Contains no cycles,
Yeah.
okay? But it's not just that.
Two paths to one node.
Okay, what about this edge here? If I add this edge, would that still be a tree? If you add the the green edge, would this still be a tree?
No, because you have
No.
a cycle.
Well, it's not a cycle because it's directed,
But
right?
it's directed.
But you have more than one path to go from one vertex to another vertex. So why do you think this is not possible using our algorithm? It has to do with the algorithm itself.
There's only one shortest path.
There's only one shortest path, but there can be equal paths. There can be paths of equal distance, right? No. But I'm saying that we only keep track of one. We do not keep track of all parallel paths from one vertex to a destination. Yep.
You can't have a child that is a parent to a parent. That's.
But why? But that's a property of a tree. But what in the algorithm makes the solution a tree itself?
Like a new short path is bound, like the old one.
Yep, exactly. It has to do with the combination of these two lines. We remove the old one, and then when we insert, we only insert one edge back into E prime. In other words, when you look at how many edges can go out of a particular vertex, it's only up to one. Let me say that one more time, because this by itself guarantees that G prime is a forest. I'll say that one more time. When you look at G prime, which is all the vertices that we already have, but E prime, which is all the vertices that we put into E prime, the only thing that we put into E prime is through this line here. Okay? And I'm claiming that for every vertex, it can only have up to one outgoing edge represented in E prime. There cannot be two or more. Because every single time before we do this, we perform this loop here. We remove everything in E prime that starts from W. And then we replace it with a single edge. So that guarantees that when we're all done, E prime can only have up to one single edge from a particular vertex, from any vertex. There can only be up to one edge coming out of it. Is that okay? And because of that, we can also then guarantee that something like this cannot happen. Because when you look at this, which is not a tree, there are two vertices coming out of this vertex here. If you have the restriction of each vertex can only have one outgoing vertex, one outgoing edge, then you can only have a tree. You can have a forest, okay? A forest basically means you can have another destination vertex which has its own tree. That's fine. That is not a problem. You can have yet another destination here that has a degenerated tree which only has one single vertex going into the destination. This can be E prime, okay? Minus the green line, okay? If you don't consider the green line and only the red lines, that can be your E prime. I mean G prime, which has all the vertices, but it only has trees. Is that okay? So Dijkstra's algorithm has some kind of interesting side effects. It constructs trees. Now, trees are also very useful. They're very interesting in many ways, but we'll leave the discussion of that up to the next class. So at this point, the first thing you want to do is to review the algorithm and see if you can apply that to the homework assignment. Okay? I did not have enough time to go through an example in today's class, but I will definitely do that on Wednesday. And I forgot to hand out the test. I have everything, destapled, photocopied, and then restapled.